I will begin. Dearly Father, we thank you for this day. I thank you for your students. I ask you to bless this work today. Help us to be able to think clearly to solve the problem in front of us, Lord. In your name I pray. Amen. All right, so setting that distraction aside, I want to show you a calculation that Professor Lopez Gonzalez shared with me. And so here it is. So we have, let's say A, curses, A, which we're thinking of as R2. B, it's a linear space endowed with the product. And he likes to define the product in terms of structure constants. So we have EI times EJ is equal to the sum k equals 1 to 2, since we're looking at two-dimensional algebra, of Cijk bk. All right. So essentially, extend that linearly. That defines the algebra. That tells you how to multiply E1 times E2. We're using E1 and E2 in the usual sense. Standard basis of R2. All right. Then, so definition or result, whatever you want to, however you want to view it, if F equals to F1, F2, then F is algebraizable when, well, I'm saying this wrong. I want to assume that this is differentiable. On R2. I mean, of course, we could restrict to like an open subset and do these things, but I'm not really interested in that at the moment, so I'm just assuming the domain of the function's the whole deal. We can restrict later if we need to. So it's real differentiable in the Fréchet sense, all right? And then we say F is algebraizable if the component functions satisfy the generalized Cauchy-Riemann equations. And so the way that looks is the following. Partial F, partial partial big F, actually, E2 equal to partial big F, partial Y, E1. This is a kind of sneaky way of writing the Cauchy-Riemann equations. So this is a nice, really nice way of writing the Cauchy-Riemann equations, because it essentially says that differentiation is just like algebra multiplication in this sort of natural sense. I mean, I'm trading multiplication for E2 for differentiation by Y, and I'm trading differentiation for X for multiplication by E1. Here, X and Y are the coordinates paired with E1 and E2, right? So I mean, this assumes, of course, that a typical point, we're using coordinates X, Y, and R2, all right? I sometimes call these the symmetric Cauchy-Riemann equations. If you look at them at the component level, what does it say? It says, if we look at it in this kind of notation, what we've got is partial X of F1, comma, partial X of F2, right? And maybe I should write that. I should really write that. Sorry, I need to hurry a little bit. Otherwise, we're not going to get to the point. Partial X F1, E1, plus partial X F2, E2. That's what this is, right? We multiply that by E2. And that's equal to, well, partial Y F1 E1 plus partial Y F2 E2. Then I multiply that by that E1. Okay? Now, what can we do here? We can multiply out, right? So if you look at that, what we got here is we've got partial f1, partial x, e1, e2, plus partial f2, partial x, e2, e2, equals to partial f1, partial y, e1, e1, plus partial f2, partial y, e2. And here's where I fess up, commutative. We're assuming commutative. Is there any loss of generality there for the two-dimensional case? Can we have a two-dimensional non-commutative algebra that's also associative?
I mean, they all have to be.
Right. There's something to think about there in going up the chain. Higher dimensions, this argument needs a little bit more care. But anyway, great. And then what we do is we take these guys and expand them in terms of the structure constants. Okay? This, of course, is all, well, it's equal. Yeah? And so this is C12, excuse me, it's C121 E1 plus C122 E2. This gives us C221 E1 plus C222 E2. This gives us C111 E1 plus C112 E2. This one, of course, expands into C121 E1 plus C122 E2. All right. Then the next thing we do is just to write this all out, collecting E1 terms and collecting E2 terms. So I'm going to put everything with E1 together, put everything with E2 together. All right? So, let's see here. So we've got C121 partial F1 partial X plus what? C221 partial F2 partial X minus C111 partial F1 partial Y minus C121 partial F2 partial Y, all times E1 plus parentheses. Same thing for E2, right? So like E2, what do I got? I'm put it down here. C122 partial F1 partial X plus C222 partial F2 partial X minus C112 partial F1 partial Y minus C122 partial F2 partial Y. Close parentheses, there's my E2 equal to 0. So that's what the Cauchy-Riemann equations look like for arbitrary structure constants, two-dimensional case. So far, so good. I have no complaints. Makes perfect sense to me. It's all good. All right? Then, because we get sick of writing F1 and F2, we introduced shorthand. We let F1 equals to U and F2 equals to V. I will make my U with a loop. I will make my V without a loop so you can see the difference. Okay? And so then, if you look at that, and you look at the E1 equation, And so this is a vector equation. The things in parentheses have to separately vanish, right? So we have C121 ux plus C221 vx minus C111 uy minus C121 vy equals to 0. And from E2, we find that C122 ux plus C222 vx minus C112 vy, oh, sorry, not vy, but uy, minus C122 vy equals to 0. Again, I have no objection. Do my details look right to you guys? So at this point, he goes, wait a second. You can look at this as two linear equations and four unknowns. What are the four unknowns? So you got like ux here, you got vx, you got uy, you got vy, right? So we can abbreviate this with columns that represent, you know, these partial derivatives, right? And just keep the coefficients. What are the coefficients we got? Again, C121, C221, minus C111, minus C121, C122, C222, minus C112, minus C122. So really, you could think about what we're doing as relating to the null space of this 2x4 matrix. I mean, okay, this is where I start to lose it. So you know, if I guess my question is, how can I be sure? What is the significance? What happens when I do row operations here? I mean, he claims, and I don't think this is wrong, but he claims that if we do, you know, elementary row operations to this system, it takes us to a new system of partial differential equations which is equivalent to the given one in the sense that it has the same solution set. So, you know, that's a theorem, right? Maybe that's a theorem we could prove for a second here. What's the theorem? The theorem is that if I have, I mean, how could we write this more theoretically? I mean, this is, I mean, equation 1, what are these? These are really polynomials in what? We're looking at L1. Here we're looking at L1 and L2. Elements of what? Elements of the ring of formal polynomials in the partial differentiation operators. Oh, it's not quite that. It's not quite that. It's not quite well, I guess maybe I could look at it this way. It's, polynomials in the sense of you've got like partial x, comma 0. You've got partial y, comma 0. You've got partial, 0 partial x, and you've got 0 partial y. Where those differential operators, for example, partial x comma 0 acting on u comma v equals to partial xu. Could we define such a thing? I mean, if I made such a definition, it seems to me that the first equation could reasonably be rewritten as C121, partial x comma 0 plus C221, 0 comma partial x plus minus C111 partial y comma 0 minus C121 0 comma partial y, right? This operator acting on uv. Would that be legit if I make, I'm really out on a limb here, guys. I'm not sure what I'm doing makes sense. My goal right now is to understand these partial differential equations as being the kernel of a linear operator. And so if I can see them as the kernel of a linear operator, then I know that the sum of solutions should be a solution, and I can do things like, so what I'm trying to say is if I can come up with a formalism which takes my system of PDEs and rewrites it as something like L1 of, f equals to 0 and L2 of f equals to 0, cutting through the noise, then it's pretty clear that if you have, these are linear operators, then you have things like any non-zero constant, c times L1, of f is also equal to 0, right? And also if you look at things like L1 plus L2, well, that acting on f is also equal to 0. And I think if you sort through it, you have essentially all of the elementary row operations. Now, the question is it the same solution set? I'm really thinking of an if-then structure right now. I'm assuming it is a solution for the given problem. It's also a solution for like c times L1, or the sum of L1 and L2, which would be like adding the differential equations, which would correspond to adding the coefficients, right? So how can you go the other way? Well, you can go the other way because elementary row operations are reversible. So if I have that these are 0, I can then do the opposite row operations and get back that the initial two were 0, just the same. So this theorem that elementary row operations on partial differential equations don't change the solution set, we can achieve this theorem if we can just see the differential equations as being the kernel of linear maps. Maybe I've done that already? What do you guys think? I don't know. I'm a little worried. Do you understand my definition, King? Yeah, like, do you buy my story that this is like that L1 up there, and when this acts on UV, according to rules like this, and also for example. Find the kernel of it. Oh no, I don't really want. I mean, finding the kernel is the whole. I mean, the kernel is what we're after, but that's if I can show that they're linear operators, which are. I mean, if being in the kernel of a linear operator is equivalent to solving the differential equation, then that's all I need. Right. The C's are just constants. They're structure constants, yeah. It's in their name. So I should think about this some more, but I think that's essentially a sketch of a proof of the theorem. I'm sure what he's saying is well known to PDE people, that if we have linearly equivalent systems of PDEs, they have the same solution set. In other words, you have a linear system of first-order PDEs. You can do row operations on them, essentially, and not change the solution set. Oh, I think it is. I'm just worried that I'm glossing over something here. Okay, all right. So we believe that doing elementary row operations to that system does not change the solution set. So if we can solve the original system of Cauchy-Riemann equations, I mean, in other words, if I can solve a modified version of these, then by this logic, I should be able to take that given solution and plug it back into the original Cauchy-Riemann equations and solve that. Right? That's the theorem. So then what he does is just to look at specific cases for the structure constants and sees what that looks like. So let's see here. You could also write these in terms of the composite of just differentiation operators and projections. Projections are linear operators. Differentiation is linear. It's the composite of projections and linear and differentiation, so it's definitely linear. Because that's what, I mean, this is the composite of, what is this? This is like the composite of the projection onto the first component map and the partial differentiation with respect to x. That's the composite of linear maps, which is once more linear. So certainly those are linear. But anyway, okay. This down here is really more the point, is that, yeah. All right. So what would you do next if you were trying to say, okay, here's a system, 4 equations, 4 unknowns, 2 equations, 4 unknowns. What condition would you look at in order to simplify this? You notice that this isn't, in principle, two-dimensional algebra has, it's Cij, right? I has 2 values, j has 2 values, k has 2 values. That should be how many structure constants? 8. And yet how many do we have written there? 6. That's because we're assuming that 1, 2, and 2, 1 are the same. So that reduces the number by 2. Commutativity reduces the number by 2. And so there are really only 6 independent components here, right? Because, by the way, this and that are the same. What else do we know about elementary row operations? The column correspondence property, right? So whatever you do, whatever happens in column 1 is minus what happens in column 4, or vice versa. Okay, so his next move is to suppose that either C121 or C122 is not equal to 0. Suppose one of these guys is not equal to 0. Then what can you do? He says, then we can do row operations to convert this to 1, 0, and then stuff. I'll try to stick with his letters in the thing he sent me, A, B, C, D, but it's A, B, C, D. You know what happens with the fourth column? It's minus 1, 0, right? So that's row equivalent to the original one in this case. And then what does he say? He says make, continuing, if B is not equal to 0, then what can you do? That's equivalent to what? 1, 0. If B is non-zero, that means B is a pivot. That's a linearly independent. That's going to be 0, 1, right? And then we get, that's funny, now he puts A and D over here. So he's changing the definition of A and D. Huh. That might be part of my confusion. Huh. Well, I mean, I guess it doesn't, I mean, they shouldn't be have any connection to the previous letters, right? I mean, there's some kind of, he puts A and D here, but I don't think that you should think of those as the same A and D, right? Suffer through the row reduction with the structure constants, yeah.
I mean, it would show you that like D is this divided by that plus whatever.
That's an interesting idea. That would take me longer than we have. Yeah. So his point, he claims at this point that we get case 1 of the algebraizability of planar vector fields paper. This is case 1. All right, well, let me write down for you what case 1 is. Since you guys don't have that paper memorized, strangely enough. Let's see here. So, all right. All right, all right. So his case 1, it says that the algebra has the following multiplication rule: E1, E2, E1, E2, E1, E2, E2, minus B, E1, plus A, E2. Again, I don't think we should read too much into A being that A or anything like that. All right, so trying to find, come on. And that, so he tells us, in fact, the Cauchy-Riemann equations, the generalized Cauchy-Riemann equations, and I'm going to translate, this is from his page 7. We've got ux plus a vx minus vy equals to 0, and uy plus b vx equal to 0. I mean, he claims that this multiplication gives you these Cauchy-Riemann equations, right? That's the claim. But before I even check on that, we could check on that, but is this, do you agree? Do you agree with this correspondence here, guys? I mean, what does that system mean in terms of the partial derivatives? It means ux, right, plus a times uy minus vy equal to 0, right? And it means what else? It means vx plus d times uy equal to 0. Am I wrong? That is not case 1. But I think it's just a typo in the PDF he sent me. I think it's actually case 2. Let's look at case 2. What is case 2? To be fair, that doesn't dispel his argument. It just means that he has a typo in the PDF he sent me. He said case 1 where he meant case 2, I think, is all it is. But I'm at that kind of point. You know when you have this point of indecision, typos seem like they're more than they are? So that's where I am. Here's the case 2. I'm trying to leave that. I'm trying to escape that. That's not where I want to live. I want to live in the world where I have confidence in what I'm doing. See, this is, dang it. See, his case 2 is, all right. I can't explain what I got to say here. It's nothing bad. It's just, it has to do with, stink. Well, curses. The type 2 Cauchy-Riemann equations are ux plus a uy minus vy equal to 0, and also vx equal to 0. I told some of you that he eliminated a parameter in this case, somewhat artificially, for the sake of making the theorem precise. That's hurting our understanding right now, unfortunately. I mean, it's making it hard for me to see. But I think, right, so that is this. Let me give this name. Look at star. Look at this. That's star. So definitely that row reduction is the first Cauchy-Riemann equation of case 2. And if you can see it, this is this, where D has been zeroed out, I would say artificially. He has a good reason for doing it, and he explained it to me. But, yeah. So I think we're in case 2. So far, so good? All right. So, okay, so what else could happen? Again, sticking with the larger logic tree, decision tree, whatever. I haven't had graph theory. You guys tell me. We're in this case still, okay? But I want to say, well, what if B is equal to 0? Suppose B equals to 0. Then what do we got? We've got, we've got 1, A, C, minus 1, 0, 0, D, 0, right? What do we need in this case then? We must have D is what? By the way, you can argue that you have to have independent Cauchy-Riemann equations, because to not have that is to violate the structure of the regular representation. I can't explain that quickly, but essentially the regular representation, because it's unitary, is a faithful representation, which means that the regular representation is two-dimensional. It's a set of It's a two-dimensional set of 2x2 matrices. The Cauchy-Riemann equations are equations that the components of the regular representation have to satisfy. So you have 4 components. It's a 2x2 matrix. To get a two-dimensional subspace, you need 2 independent equations. If you only had one, you'd have a 3-dimensional subspace, which would violate the faithful thing that I just talked about. So we need linear independence of these rows. We have no choice. It has to be the case that D is what? Yeah, D has to be non-zero, right? And so this is equivalent to what? Now that, what set of Cauchy-Riemann equations does that give me? We've got, what's our notation here? Ux plus a what? Vx minus what? Vy equals to 0, and what's that again? Uy. Well, that's half a case 1. I mean, this is this, right? That's the first Cauchy-Riemann equation in his case 1, according to the planar vector field paper. But, man, this is... oh, look! Yeah, B is equal to 0. Huh. No, he doesn't assume that B is equal to 0 in that paper. Well, my point is that in case 1, whatever b means there, if to put that b to is bb. Is bb is a good question. Gah. I just know I can match up the second equation in case 1 if I put b equal to 0 there. Whether or not that has any direct connection to this b being 0, I'm not sure, honestly.
So it's with Vx, which is in equation 2, which is the one you assume to be 0.
Where? What?
So
Where was the b?
you have in case
Oh, it's in the
it's in the Vx position, which is the same position as the B.
But you got to remember that that b, it was not the same b. Good grief, how to say this?
I see what you did. Yeah, it's probably.
Dang it. Oh no, you're right. You're right. You're right. It's coming from there, which was the Vx. But you're right. It's still the original meaning of. You're right. It is connected to Vx. There's hope that b is b. All right. So I'm a little bit bothered that I don't feel like I've quite reproduced his cases. All right. So I'm struggling with that. It doesn't seem, well, I suspect it's just something stupid on my part, not seeing something just silly. Why these aren't exactly the same and why that's not a problem. One thing bothering me, okay? Then what's next? What's left? The other case. In the row reduction. What are the other possible row reductions of such a matrix? Well, the first column might not be a pivot column, right? So if the first column's not a pivot column, the other case, and this is the one case I feel like I really mostly understand, would be is if C111 equals C, what is it? C, no, 121 and 122, rather. If they're both 0, you've got something like this, right? Which corresponds to something like, A Vx plus B Uy equals to 0 and, C Vx plus D Uy equals to 0, where the determinant of A, B, C, D must be not equal to 0. Of course, this is equivalent which give us directly that Vx equal to 0 and Uy equals to 0. Which you can recognize as saying U is just a function of x and V is just a function of y. Maybe you remember that's the Cauchy-Riemann equations for the direct product algebra. So here's the thing that bugs me. All right, let me try to explain my problem to you. Maybe explaining it to you will just free my mind of whatever it is. I got some hang up. Hang up I can't get over. I think we're past all this here, right? Okay. So here's the problem we're working on, guys. Well, maybe I don't even have to. Well, fine. So one of the problems we're working on is ux equals to some function of u and v. Vx is equal to some function, g rather, of u and v. And we're trying to decide when you can take this system, right, And you can rewrite this as basically, well, there's a couple different things going on, but here's one. Ux, Vx, f comma g. And if the algebra is right, we can look at this as dw dz equals to f of w, where z is equal to x comma y, so to speak, and w is equal to u comma v. Now, all right. I guess you can see it. Can you guys see it? Now, I would argue that this is just a typo. This is really case 2, right? I think we could say that's actually case 2, no big deal. And you know what? The other row reduction, it's case 1 up to some issue with parameters I don't quite understand. Again, not that big a deal, I hope. What's the unit for case 1? What's the identity in the algebra for case 1? If you look at, yeah, it's E1. You can see it, right? What's the identity in case 2? It's E2. So this is what's in the other notation that he sets up in the other paper. Is what leads to the R equals 1 or the R equals 2 families of algebras, where he uses P1 and P2 rather than this A and B and junk to sort through the cases, as I understand it, or don't understand it. It remains to be seen. And then, of course, over here, once you get to this guy, well, that's the unity for the algebra is actually E1 plus E2. Right? So I guess what he's saying is that all right. Suppose I had, all right, I guess I could say this. I think I could put it into words now. I made progress. I just made progress. If I have a function which is adifferentiable, if f equal to u comma v is adifferentiable, then then u comma v solve star. Right? Thus, u comma v solve either case 1, 2, or the E1 plus E2 equal to 1A case. Is that a fair statement? That's what I want to ask you guys. I'm not saying that algebra has unit E1 or E2. That's an arbitrary algebra, two-dimensional algebra. So that means its component functions u and v solve star, which means that they will solve any row equivalent system to star. So I think what he's arguing is that if you look at all possible row equivalent matrices, there are three cases. It's either case 1, case 2, or that guy. And so if I check if my given pair of functions, u and v, if I check if they solve either case 1, case 2, or case 3, then I know if they're going to solve something. So one of the things that says to me is that if I've got an algebra where the unit is not E1 or E2, but if the unit's something funky, like E1 plus 2E2, then if it's got that kind of differentiability, it's also got either case 1, case 2, or case 3 differentiability as well. That runs counter to my intuition. And yet I don't see the hole in the argument.
Well, if those are the only possible solutions, then how could it be? I mean, if you had your E1 plus 2E2, would it just not solve those equations? How would do that?
No, that's the point is, can we construct a two-dimensional do we have time to construct a two-dimensional algebra with the unit E1 plus 2E2? Yeah, we do. All right, let's do it. If my intuition is right, it'll be a counterexample. It won't solve any of the cases, and then we'll know something is amiss with our argument. So that's why I was looking at the isomorphic stuff earlier, because I thought I could conjugate the regular representation and then work backwards, but I don't know if that makes sense.
You're saying it should solve them.
Yeah, I want to believe he's right. I want to believe
You're
I'm...
saying it should solve them.
I mean, he has... I feel like he's implied that. What he says is that case 1, case 2, case 3 does not cover all possible two-dimensional algebras, but it does cover all possible algebrizable vector fields. So it suffices to look through this class of algebras to check, even though it's not all algebras, which is bothersome to me. I will get over it eventually. I need a place to work. Did you get this? You got this, right? Yeah, okay. All right, so how about... never good. Never a good smell. Okay, so we want to have A with the 1. We decided 1, 2, right? Okay. So what's that tell us? That tells us that we need 1, 2. Well, rather we need E1 plus 2E2 times A E1, let me say X E1 plus Y E2 to equal to X E1 plus Y E2, right? That's what it means for it to be the identity. It times anything gives us back the anything. What does that actually tell us about the multiplication? We've got X E1 E1 plus 2x plus y E1 E2 plus 2y E2 E2, right, equal to x E1 plus x E2. Oh, sorry. All right. So then what? I mean, to define this algebra, right? I need to tell you. We need to decide. Well, yeah, fine. I mean, I want to write the multiplication table for this, really. Kang, do you have any insight into this? We're trying to come up with an algebra that has unit 1, 2. The unit is 1, comma 2. I don't much care beyond that. I just want it to have unit 1, comma 2, and to be unital and associative. I feel like the laziest thing we could do would be to think of the, what's that? The
So the multiplication between x, y, and a, b is the multiplication between x minus 1. No. I mean, you have a algebra elsewhere that component wise multiplication. You shift from the point 1, 1 as a unit to 1, 2, and the other
So you're thinking of this as a
combination.
twist of the direct product.
I mean, like, it's still isomorphic to R squared, but like the shifted version.
Yeah. Oh, how about the null numbers? If we did, I mean, wait, can you tell me what to write down here? The multiplication table for this algebra.
Oh, you need to do all
Because I need that to write down the Cauchy-Riemann equations. Yeah.
So I suggest E1 times E1 to be equal to 1, 1.
Okay.
And E1 times E2 is 0.
0.
And E2 times E2 is also 0.
Just like that. So what's the unit in this? What's the unit in here? One,
Yeah, I consider 1, 2 as
1, 2 is the unit. So if I